going to talk about the crystalline version of TVs.
Thank you. I think I'll not use it today. All right, so today we'll have an overview. There will be no results taken maybe yesterday evening or something like that, no new results. This will be essentially an overview of how liquid crystalline ordering can be used in photovoltaics, in particular for the control of morphology. So I'm from the University of Colorado at Boulder, with the Liquid Crystal Materials Research Center, Department of Physics, and also RASEI. So I would like to start from clicker questions, so please have those ready. The first time I'll give you just a little bit more time than you need, since you need to turn on your clickers. And so the system is ready. Please start voting. So we'll see who is attending lectures and is always on time, right? This is the first question I have to you. So is it clear? Can everybody read? Okay, I see some 23 volts already, 24. I'll stop the system in just a second. So let me display the results. So most people answered E, and this is actually the answer I expected you to give. So A, B, and C are all true, right? Those are all examples of self-organization when we don't do something special in order for this to happen, right? So in the case of, you ICOM students going, self-organizing yourself and going for a trip, right? We organizers do not have to really do much, right? You like to do it, you do it on your own. And we like that because it would be a lot of time for us to plan an activity like, for example, whitewater rafting, right? And organize everything for you. So it's much better if you do it yourself. Likewise, you can have similar type of self-organization in molecular and colloidal systems, where the useful structures can emerge without much work. In other words, we would not need to use nanofabrication, for example, to produce some sophisticated nanoscale structures, right? Rather than that, we would simply use self-organization of molecules that form certain thermodynamically stable phases, right, and organize themselves into structures that can be useful for different applications. And those can be useful in particular also for PV applications too. So yes, E is correct. And the question is, can we utilize molecular or colloidal self-assembly in PV applications in particular, obviously? Liquid crystals are a classic example of self-organization when molecules form a number of different phases spontaneously, right? Those are thermodynamically stable phases, in relation to PV applications, I just want to give you an example how liquid crystal display technology perhaps was very useful to build the trust in organic photovoltaic materials, right? So you know that liquid crystal displays is a mature technology nowadays, and hundreds of billions of dollars worldwide this is a display industry with hundreds of billions of dollars in it, right? So you obviously can see those displays everywhere in large area flat panel TVs, like those, for example, or in the case of your iPhones, you too utilize liquid crystal displays. And so obviously in all of those cases, you have pretty high intensities of light, right? Just like in the case of organic photovoltaics, many years ago, people worried that liquid crystals might be not good enough for display applications because they would not be stable enough, right? Under long-term light illumination, perhaps they would decompose, right? And so yet, this doesn't happen. We use LCDs all the time. You never need to worry about liquid crystal decomposing or something like that to happen. And very similar kinds of molecules are also used in photovoltaics, right? So obviously, organic light-emitting diodes further helps to build this confidence that organic materials can be stable under long-term illuminations with pretty high intensities of light. So let me proceed with giving you a very brief background into what liquid crystals are, right? So those materials stand in between the crystalline solids, which have perfect order, and isotropic liquids, which have no order at all, but are fluid instead, right? So liquid crystals have some degrees of ordering, and if you have three-dimensional translational and positional ordering, it's not a liquid crystal, but rather crystal. At the same time, they can flow just like fluids do, right? And so, for example, in this classic example of nematic liquid crystal, the molecules align spontaneously on average along this direction, which we call director. Now, as I already mentioned, there is only partial ordering. So in this particular case of nematic liquid crystal, you only have orientational ordering, but no positional ordering. That's why this material can flow. And if you were to follow the centers of mass of those anisotropic molecules, you would realize there is no correlation between those centers of mass. So there is no translational positional ordering that you could find in here. Now, what are the driving forces for self-organization of those molecules into those different kinds of mesomorphic phases, the way we call them? Well, so there are two major ones, and I'll not be able to describe all of them, but two major ones are the following. So first of all, when you have anisotropic molecules with pretty high aspect ratios that look rod-like molecules, then the van der Waals forces are highly anisotropic, right? And they typically drive this self-organization into liquid crystal phases in pure materials where the entire system could be composed of one chemical, right? Just like in this case in here. So the interactions between them are highly anisotropic, induced dipole-dipole interactions, and they lead to this organization. Obviously, as you would increase temperature in such a system, the interactions, those anisotropic interactions, would become weaker than thermal fluctuations, and the system would melt, right? If you would decrease temperature in such a system, it may crystallize, right? And so one interesting feature that those materials have, therefore, is that they can self-assemble, and as you crystallize them by lowering temperature, for example, they can preserve this ordering. So it's easy to order them when they're in a liquid crystal phase, but then you can take advantage of this ordering as they crystallize too. Okay, the other very common driving force is the so-called static interactions. Those are also entropic interactions between the particles, that have highly anisotropic shapes when they are dispersed in a solvent, right? So imagine you have rods that are rigid and therefore cannot penetrate each other, right? So the particles, like you can see in here, will maximize their entropy when translational entropy, when they are aligned parallel to each other, right? Obviously, this type of ordering allows you to have more choices in terms of the positions of the center of mass than this one, because each time when the rod-like molecules or particles would align perpendicular to each other, you have a large excluded volume that the center of mass of this one cannot penetrate into because of presence of the other one, right? And so you therefore maximize translational entropy, although you compromise orientational entropy in this case, and that leads to spontaneous formation of liquid crystal phases. Okay, so we therefore can already classify liquid crystals based on how they are formed. Right? The ones which are formed in solutions where you have molecules or particles dispersed in some solvent, they are called lyotropic liquid crystals. The ones which are formed by molecules when you have 100% the same material or very similar materials are called thermotropic liquid crystals. And in those cases, you have formation of liquid crystal phases as a function of temperature. Right? Now, important feature of all liquid crystals is that the molecules are highly anisotropic. Right? And so rod-like molecules and disc-like molecules, for example, can form so-called nematic phases that we already saw. Right? Those would be, typical chemical compounds. And you can see that in one case, those all rod-like molecules on average point in the same direction, right? Although the scalar order parameter is not unity, it would be unity in a solid crystal. It's somewhere between 0 and 1, right? And also, likewise, disc-like molecules can form Discotic nematic liquid crystal phase, where all the normals to the molecules point in the same direction. Now, you can have not only liquid crystal phases having just orientational ordering, but also phases that have both translational and orientational ordering, but it should be partial ordering, right? Because as I already mentioned, when you have both three-dimensional orientational ordering and translational positional ordering, this would be a crystal, not liquid crystal anymore in that point. And so one example is having layered structure on top of orientational ordering, right? And that's what you can see in here, for example. So in nematic phase, you just have orientational ordering so that molecules point on average in the same direction. Now, if they also start forming phases, forming layers like those you see in here, this is now called smectic phase, and it has one-dimensional positional ordering, right? So if you would go in the direction along this director, right, with the double arrow, denoting it, you would realize that there is periodic change of density, right? So you have now one-dimensional positional ordering and two-dimensional fluid, because the molecules can freely move with respect to each other within the layers, but cannot jump across the layers. Now, if you tilt those molecules, you form the so-called smectic C phase, right? And so now this can become biaxial because the normal two layers and the average orientation of molecules are in different directions. Now, when you have disc-like molecules, similar to the ones you see in here, where R stands for some radicals that can be different hydrocarbon tails, for example, you realize that you can form not only Discotic nematic phase, but also columnar phase. And in here you can see a schematic representation of such a phase. This is just the simplest phase, but many, many other phases can form, and we just simply don't have enough time to discuss them. But what you see in here is that you have now not only orientational ordering, but also two-dimensional positional ordering, right? So in the plane perpendicular to the normal to those disc-like molecules, you have hexagonal periodic pattern of their organization. But this material still can flow because the columns can slide with respect to each other, right? And it's still fluid. You can pour it from one bottle to the other, for example. And now, obviously, many exciting PV applications take advantage of polymers, right? We all, I think by now, know what polymers are and what kinds of polymers, like side chain, main chain polymers, one can have. Well, it turns out polymers can form a number of liquid crystal phases too, right? So the only difference compared to the small molecules phases I was discussing before is that now those anisotropic rod-like or disc-like units are interconnected with each other, right? And so you again can form both nematic and smectic and columnar phases and all phases that small molecules can form as well, right? So the only difference, as I already mentioned, is that they are linked to each other. All right, now you can have also different kinds of linking, and if the molecules are allowed to rotate in those polymerized systems, but not really move much with respect to each other, yet they can freely rotate, then you can form nematic elastomers or rubbers, right? And so in here you can see, again, all kinds of phases that small molecules can form also can be formed by those systems. And then interesting property of such systems is that there is a coupling between orientational ordering and shape of materials in those systems. So now, in addition to that, I'll just very briefly mention, I'm sure that all of you dealt with liquid crystal when you were washing your hands today, right? Because if you simply dissolve soaps, they spontaneously can form micelles. Micelles can spontaneously form a number of those different phases that we have seen already, right? And you can have cylindrical micelles, for example, that will form hexagonal columnar phases, or Discotic nematic phases, or cubic phases with liquid crystalline, different types of ordering. Moreover, I'm thinking that many of you might have had some liquid crystals for breakfast, just because molecules like the one you can see in here are oftentimes used as food colorants and also as dyes. And therefore, when you disperse them in liquid crystal at somewhat high concentrations, they can stack on top of each other, self-organize into those type of stacks or aggregates that then spontaneously form nematic or columnar hexagonal phases and many other phases. Now, a number of anisotropic nanoparticles, like for example, and this is not well visible, so for example, cadmium selenide nanorods or carbon nanotubes, when properly dispersed, can also form liquid crystalline phases. All right, now, so far we did not really discuss systems that are PV related, right, or PV related. However, you all know that perhaps the most famous PV system is P3HT PCBM that we already heard about quite a lot during this summer school. So you can see the chemical structure of materials that you already know a lot about. So I have a question to you, a clicker question that I want to ask before I proceed with discussing in more details. So the system is on. This time you have just half a minute or so. Please be quick. All right, I see some 35 volts already. I'll stop the system in a second. Don't think too hard. Just, okay, I'm stopping the system. All right, so most people answered A, that's 41%, but C and D were quite popular answers too. Well, the answer is yes, and most of you answered correctly. So the P3HT can actually form not only thermotropic phases, which would be at pretty high temperatures, above 100 degrees C, and this is well documented in literature and many papers you can see over the course of 20 years or so, or maybe less than 20, 10 years, I guess. Then it also can form lytropic liquid crystal phases in different kinds of solvents, and this is just also one example of an article fairly recent that is discussing how as you evaporate solvent, you spontaneously can form a liquid crystal phase, right, at a certain concentration range. Obviously, your concentration changes as you evaporate your solvent, and at a certain moment you reach the lytropic liquid crystal phases of different kinds, right? So one more clicker question for you. I mean, is it relevant? Is it important? I already mentioned that the thermotropic phase is at pretty high temperature. Well, you know, maybe you don't really keep your solar cell at that high temperature, obviously, but can it be important still? Now, lytropic phase I mentioned is in a solvent, right? And although you don't have a solvent in the actual PV device, but you do use solvents in preparation. So I hope this gives some hints for you to answer the question. And so most people answer D. This is exactly what I expected. Yes, indeed, we do care about morphology, right? The OPV performance is almost all about morphology. Chemical structures, of course, are important too, but once you have them, you do really care about morphology. And we already all know that what you would ideally want to achieve in your device is something like this, where you would have this nanoscale phase separation, right? And the size of domains would be roughly comparable to the exciton diffusion lengths. Now, if you were to have good charge carrier mobilities, what you could also do is you could have somewhat thicker devices, maybe absorb more light, right? That would be good to achieve too. And so what that means is you might care about the ordering in such systems. So first of all, you care about the length scale of separation and on the nanoscale here, and also about the ordering that will somewhat determine the charge carrier mobilities. And we'll discuss that a little bit later, but before we do that, I want to go back to some ideas that emerged perhaps between 20 and 10 years ago, but never have been really utilized, I think, to the full extent, right? So many of you might have seen this interesting work in here, and there have been other works even before that, where people proposed the use of self-assembly, liquid crystalline, columnar, hexagonal self-assembly in PV applications, and at that time they achieved fairly reasonable for that time efficiencies which were on the order of 2%. Right? So those would be the types of molecules utilized. You can see this is not heterojunction, it's based on small molecules, and you just have hole accepting and electron accepting monolayers in here and an interface between them. Now, the molecules of this kind can form not only just columnar hexagonal phases, but also a number of other different phases, right? And they all would have both liquid crystal and crystal phases. And what's interesting is that as long as you achieve certain desired liquid crystal self-assembly and alignment, you can then preserve that alignment as you go to, for example, lower temperature crystalline phase, right? So a liquid crystal is essentially the means for you to achieve desired alignment and morphology. This is not quite well visible, but there have been two different approaches discussed in literature fairly extensively that would utilize different types of mesophases that you can see in here, right? Starting from the mesophase with lower ordering where you achieve the desired alignment of molecules, and then you crystallize them because you get even better charge mobilities as you go to the crystalline phase, right? And so as you would change temperature, you can achieve all of those phases with different degrees of ordering. The more perfect crystalline ordering you have, the better charge mobilities you get, and that's what you want. So now, going back to the columnar self-organization, the first approach, which I already showed, was just using two monolayers and the interface in between them, where you have just donor and acceptor. Obviously, the area in this case is somewhat smaller than what you might want to have, right? And what we typically have in the case of polymer PVs. Now, however, you can also have columns running across the thickness of such a PV layer, as you can see in here, and some of them can be made of molecules that are acceptors, and some of them are made of molecules that are donors. But this is, so although this type of geometry has been really successfully utilized, and efficiencies over 3% have been documented in those cases, for example, in the recent work that you can see in here. But the other morphology was less successfully utilized, and I'll discuss the reasons for that in just a minute or two, but there is still, I think, a lot of potential. Now, as I discussed those different phases, mesophases and crystalline phases that can form, I mentioned that the more ordering you have, the better, right? And so indeed, if you have a crystal, your charge mobilities are really great. As you make the system somewhat more disordered, for example, you go to columnar hexagonal liquid crystal phase, your charge mobilities drop, and this has been studied extensively in literature, but the charge mobilities across along the columns can be still very good. And as I already mentioned, if you achieve this type of ordering, you can then easily crystallize the system by preserving this ordering and still take advantage of high charge mobilities in the crystalline order. All right, so now all right, so now the other approach that people have been trying to pursue is often called double cable polymers, and I guess you're familiar already with this idea. The similar type of approach can be also achieved using columnar liquid crystal self-assembly, and was pursued in a number of works that I listed here. Again, the idea is that the donor and acceptor parts of molecules can be linked with each other, and then you immediately get the correct type of self-assembly, as they form columnar liquid crystal phases and then crystallize to form crystalline liquid crystal phases as you were to, for example, further decrease the temperature and increase the ordering. So here are just some examples of works that have been published. You can see already quite some time that are kind of relevant, but the challenge is, one of the challenges is to be able to achieve the correct type of ordering or alignment of such columnar systems, and also stacking into the correct type of the columns, columnar separation that we would ideally want to have from the standpoint of view of charge separation and device performance. So, instead of getting something like this, you can obviously have those other configurations that would make system much less ideal. Perhaps this could be something I would have started from the very first idea of utilizing the liquid crystalline self-assembly, and then perhaps also crystallizing the system in order to achieve even better charge mobilities was is dated back to 1987 by Brian Gregg, who is currently at Handel, where he synthesized this system that you can see here that also forms columnar phases at different temperatures. The other approach where you could take advantage of self-assembly and liquid crystallinity is related to this work that you can see here in the bottom of the page. The authors in there take advantage of the formation of liquid crystal gels that become as a template for the desired morphology, nanoscale morphology, where the donor-acceptor parts of the system separate on the nanoscale and can form fairly uniform, vertically aligned domains, right? And so the system that was utilized in this particular case is composed of those type of molecules that serve as donors. They can be polymerized by means of photopolymerization, right? So you just need to add a photoinitiator, and then those molecules in here would polymerize, while the other ones, which are fairly similar, would not polymerize, and so you would have partially polymerized system that would promote, and this would promote phase separation on the nanometer scale as well as formation of vertically aligned domains. And because in the liquid crystal phase, before you solidify the system, it's fairly easy to achieve desired alignment. You can therefore control this morphology quite relatively easily. Okay, so far I overviewed very briefly the different approaches that have been utilized in the past. One is related to small molecule systems, right, like the ones forming columnar and also smectic liquid crystals, where by means of liquid crystallinity we can achieve desired self-assembly and then crystallize a system to have desired morphology in the solid crystal state, for example. I also discussed a couple examples of how liquid crystal phases might be relevant to, for example, the morphology in polymer liquid crystals such as PCHT, PCBM system. But what I want to discuss next in the very end of my talk is how the liquid crystal display technology and PV technology could be possibly merged in the future. You might know that there is actually a lot in common between the two technologies and many types of PV technologies as well as many types of LCD technologies. And some of you might have heard that liquid crystal display manufacturers like Samsung and LG, for example, are already coming to the market, PV market as well. So before I do that, so I will briefly mention in the end the recent development in making this happen. But before I do that, I want to very briefly, explain to you how displays work, because being in PV community, you might be actually not familiar with that. So there are many different kinds of displays, just like many different kinds of PV technologies we have, right? But some of the most common and simplest ones, I'll show you very briefly now. All of them utilize polarizers, and you typically have two cross polarizers and a very thin film of liquid crystal aligned in a certain way in between, to which you apply electric field and do some switching, right? So in one case that I show in here, you have two different substrates which you treat in such a way that you align liquid crystal molecules at those substrates in well-defined directions, which are shown in here by those red double arrows. Right? What that liquid crystal do is all the molecules uniformly twist from the bottom to the top, as you can see in here. Right? Now, if you apply voltage to such a cell, and typically you just need 1 volt or so, very low voltage, you then realign all molecules along the electric field direction. Right? They are very responsive to applying external fields. Now, if you send light across this sample, right? For example, from the backlight of your liquid crystal displays in the desktop display of your iPhone, for example, then what happens is in this geometry, when no field is applied, the polarization, linear polarization of incoming light is simply following the rotation of liquid crystal molecules, so that the light can pass through and we will see that pixel being bright. Or if we have a certain color filter, we'll see it being of certain color. Now if you apply voltage, then the optical axis of this uniaxial liquid crystal is perpendicular to substrate, so polarization does not change, and between cross polarizers all light is extinct, so this pixel looks black. right?
Last 5 minutes.
Oh, okay, great. And so that's what you can see in here, demonstrated in a slightly different state for, the two different states. And you can therefore control the intensity, the amount of intensity of light passing through such a liquid crystal pixel. So this was one type of technology. Another way of doing it is you have electrodes in the plane of the liquid crystal display, and you apply voltage in between those electrodes. Therefore, you rotate those molecules, and because the sample is placed between cross polarizers again, you again control the amount of intensity of light passing through the system of cross polarizers. Right? So I hope this is obvious. You perturb orientation of optical axis of liquid crystal, and that makes the light leak between the system of two cross polarizers. Yet another example is shown in here, where initially molecules are vertical, but you have such patterned electrodes at the top and bottom. Then you apply fields, and again you distort that molecular alignment. That allows light to pass through because it changes polarization, and it therefore can pass through the system of cross polarizers because of presence of liquid crystal in between those polarizers that actually changes polarization of light. Right? And so now I have a clicker question to you again. I started the system. Why is this all relevant? You've seen in all cases you have polarizers in liquid crystal displays. They seem to be very important. How much light do we lose on the polarizers? Alright, I stopped the system. You actually run out of time, so we'll be quick. So most people answered A. I'll not even show to you the distribution, but 90%. It's correct answer. So it's a lot of light we lose, right? Can we somehow recycle that light? By, for example, integrating organic PV with the liquid crystal display. I already mentioned there is a lot in common between those two technologies, and the Yang group from UCLA is recently demonstrating, I think, very exciting development in this direction, where the PV or PV cell can be actually polarizing, and it can be therefore in future potentially integrated with liquid crystal display technologies, right? So instead of losing that 50% of light, you could perhaps recycle a fraction of it, not 100% of that, but still that would be useful because, as I already mentioned, the manufacturing, those technologies are highly compatible. Now, if you can see in here again, the two polarizers are pretty good quality, and you can distinguish a lot of light in between them. Although, if the lighting would be slightly better, you would see that there is still some coloring, so there are still obviously a lot of challenges to pursue in order to make it work in a desirable way. And what's also interesting is that there is no really super special materials in that system. It's again very similar to P3HT PCBM system that was used in this particular study for creating of this polarizing PVs. All right, and so since we run out of time, I will conclude here and maybe very quickly some questions.
We have time for a couple questions.
Are liquid crystals available in nature?
Pardon?
Liquid crystals are
Available in nature. Absolutely. We are all actually made out of liquid crystals. Well, you know that the membranes of cells are in a liquid crystal phase because if you would have a crystalline ordering in this membrane, it would be rigid and many biological processes would be impossible. If you would disrupt it, that means that your lipid molecules would be free to flow in whichever direction they want, and therefore they would, the cell would die again. Disrupted membrane, that means the death of cell, right? And molecules like DNA can form liquid crystal phases too, not the very long DNA chains, but somewhat shorter DNA chains can form liquid crystal phases. Actin, all kinds of proteins, cellulose, nanocrystals can form. So yeah, they're all around us. And I already mentioned that food colorants, dyes we use for clothes, all of that forms liquid crystal phases because there are a lot of anisotropic molecules around us, and once they have this highly anisotropic shape, interactions between become highly anisotropic too, and therefore this phase behavior is so widespread.
Thank you. In the case of P3HT, is the liquid crystal formation or the self-assembly, is it a dipole-dipole interaction or it's a hydrophobic-hydrophilic interaction? It's my second question. And my second question is that by increasing the concentration of P3HT, like, for example, the example which you mentioned for the soap, is it possible that we get various geometries?
Yeah, good questions both. So let's start from the first one. So in the case of thermotropic phase behavior, when you would have pristine 100% same material at high temperatures, there are obviously induced dipole-dipole interactions, so van der Waals interactions playing the role, not the in some lyotropic systems, like surfactant-based lyotropic liquid crystals, hydrophilic interactions are important, but not at all in this case. Now, yet, in the case of P3HT, it's not even just that, right? It's more complicated case. The small molecules that I was showing before, can be in a simple way understood using just only van der Waals anisotropic interactions. In the case of P3HT, that phase behavior when there are lamellar phases at high temperatures, that's much more complicated, and we can discuss later, but that takes time to explain in more details. What else? I forget.
By increasing the concentration, can we get other morphologies?
So now in the case of lyotropic system, I understand, because that's not 100% the same material, right? So in that case, you do have some formation of fibrillar structures, right? And the phase behavior is not fully explored because it will depend on the type of solvent you use, right? And there are only some systems that I have seen studies for. That one work I showed was just one example. So in principle, you can expect formation of both nematic-like phases formed by those fibrillar structures and also columnar hexagonal phases, perhaps of different types, because there are many of them.
In polymers, we have sometimes different lengths. So does this have an influence?
We have what?
Different lengths of the polymer can have.
Oh, sure, yes. So in the case of polymer systems, two different length scales are very important. One is persistence length, right? Persistence length is simply telling you what is the length of the molecule on which thermal energy is strong enough, is sufficient to bend this molecule into semicircle, essentially, right? So the length at which K Boltzmann T is enough to do that is called persistence length, and that's very important. But the second one is contour length, as you already mentioned, depending on whether you have flexible, semi-flexible, or fairly rigid systems, one or the other becomes more important, right? And they can be, in certain cases, comparable to each other. So yes, absolutely, because, for example, if you have, and also preparation becomes important because it can make one of those two length scales more relevant than the other, right? So, for example, if in certain preparation conditions you stretch molecules that, due to entropy reasons, flexible molecules would often tend to form globular states. If you stretch them, that's one thing. If you don't, that's a different situation. So.
All right, I think we're going to move on because we're going to be late again. Let's have a 5-minute break and then we'll continue with the next slide.